Okay, so now we have a good grasp on the concept of extreme values, absolute extrema, local extrema. And we talked about a relatively effective way to find absolute extrema via the closed interval method and the open interval method. But in order to dive in and really study the local extrema of functions more carefully, and really to get at the shape of functions, or the shape of the graph of functions, we need to discuss one of the key tools for the rest of this course, and that's the mean value theorem. And the mean value theorem is really interesting because you could probably learn all there is to know in calculus without ever mentioning the mean value theorem. But you would be missing the key piece that helps explain why everything works. The mean value theorem is really what's underneath the hood of the car, helping everything run smoothly. Now, whether or not you look underneath the hood, that's up to you. But we're going to do that right now and discuss the mean value theorem. So here's what the mean value theorem says. And not surprising, it involves a function that is continuous. Okay, so if f of x is continuous, on the closed interval a to b. Well, this sounds really familiar. This is just like the extreme value theorem. But we're also going to require a little bit more. So f of x is continuous on the closed interval ab. And, so here comes the extra condition, differentiable on the open interval a to b. So continuous on the closed interval, and then differentiable on the open interval. So in other words, f could fail to be differentiable at one of the two endpoints of the interval, or both. Then what? Then we can conclude there is a number c in the open interval, so that's important, in the open interval, such that f prime of c equals, okay, so c is in this open interval where f is differentiable, so it makes sense to talk about f prime of c. But specifically, f prime of c is equal to the average rate of change over the interval. Okay, so at first glance, this looks a little strange, but I want to show you a picture of what this is really saying. And hopefully from the picture, you get a grasp that actually geometrically, similarly to the intermediate value theorem, the mean value theorem is very natural. There's really not a lot that it's saying. It's saying something that you would probably expect to be true anyway. So let's look at a picture. Okay, so in blue, graphed right here, is the function f of x. So here's f of a, here is f of b, here's this interval a to b. Notice that f of x is continuous on this closed interval and differentiable on the open interval. And now this red line is the secant line. So this is the secant line with slope Well, remember that the secant line between 2 points on the graph, here a comma f of a and b comma f of b, so these 2 points, the secant line has slope equal to the average rate of change of the function over this interval. So the slope of this line is f of b minus f of a, so change in y over change in x. So that's the average rate of change. Okay, nothing special about that. Now what the mean value theorem says is that there is a point C that if I look at the tangent line, so this is the tangent line plotted here. So there is a tangent line for a point C between A and B for which the slope of the tangent line is equal to the slope of this secant line. So remember that the slope of this tangent line is f prime of C. So there's a point where the instantaneous rate of change inside the interval equals the average rate of change over the interval. And so hopefully this clears up what the mean value theorem is saying. There's also a really nice way to think about the mean value theorem in terms of velocity or change in position. So if you have an average velocity over a period of time, what the mean value theorem says is that actually there's a time when your instantaneous velocity equals your average velocity. Okay, so in other words, if I drive 60 miles in 1 hour, now of course that doesn't mean I'm driving 60 miles per hour over that entire hour. But what the mean value theorem guarantees is that there is at least one time in that hour for which I was driving exactly 60 miles per hour. So if I'm averaging 60 miles per hour, there has to be a time where I'm driving exactly 60 miles per hour. Okay, so I told you that the mean value theorem was crucial to the rest of the course. And now we're going to start talking about this a lot more in the next lecture when we actually use the mean value theorem to illustrate what's called the first derivative test for local extrema. But before we get there, I actually want to show you a pretty simple application of the mean value theorem that's going to come up later on in the course. And that's the concept of antiderivatives. So let me tell you first what an antiderivative is. So if f of x, now we'll use little f here, is a function, and capital F of x is another function for which f prime of x is equal to f of x for all x in some open interval, then f, capital F, is called an antiderivative of f of x. on this open interval AB. Okay, so notice the terminology here. Antiderivative. It's sort of like a backwards derivative, because if I take a backwards derivative, I get a function whose derivative is the function I started with. Okay? And so there's another keyword I want you to pay attention to here. And now this is not an English language class, but English is important for communicating ideas, at least in English. Other languages are good at communicating too, but I'm speaking to you in English, and I'm using this English word "an." And so the significance of this word "an," whether or not you know this is fine, but if I had said the, f of x is the antiderivative, then that would specify that this capital F of x were unique. There's only one. But the fact that I'm using "an" means that there could be more than one. And in fact, antiderivatives are not unique. So there are more than one function whose derivatives are a given function. So for instance, x squared, the derivative is 2x. But the derivative of x squared plus 1 is also 2x. So x squared and 2x, so let's see, so x squared and x squared plus 1 are antiderivatives of 2x. So just as an example. Okay, but the idea behind antiderivatives is very simple. We've spent all this time talking about derivatives, and now we're just saying, well, what about if I have a function? Can I find another function whose derivative is the function I started with? And it turns out the answer is yes, under mild conditions. So if the function's continuous, we'll talk about this later. And then next, the interesting thing is that these antiderivatives are not unique. But what the mean value theorem will tell us, so by the mean value theorem, we can actually say something about all the given antiderivatives of a function. If capital F and capital G are antiderivatives of some function f, then f of x, capital F of x, is equal to capital G of x plus c. Where what is c? Where c is some real number. Some fixed real number. So another way to think about this is that antiderivatives differ by a constant. And now this is a direct corollary or application of the mean value theorem. So let's see how this goes. Okay, so we want to show why antiderivatives have to differ by a constant, on some open interval at least. So suppose that capital F is an antiderivative of little f and g prime of x. is f of x. So in other words, capital G is an antiderivative of f on some open interval AB. So here's the idea. We want to let h of x be the difference between f of x and g of x. Then it is enough to show that h of x is constant. Okay, so if it's constant, this function h on this open interval AB, then we see that the difference between f and g has to be constant. So in other words, f is equal to g of x plus some constant on this interval a to b. So how are we going to do that? Well, assume there are c and d contained in this open interval AB such that, well, first we'll assume that c is less than d. That doesn't really matter. And h of c is not equal to h of d. So in other words, we're just assuming that h is not constant on AB. There's 2 points in this interval AB such that h of c is not equal to h of d. But then, by the mean value theorem, we know that there is a number z in AB such that h prime of z is equal to h of c, h of d minus h of c all over d minus c. Okay, so we just take this closed interval c to d. Because h is differentiable, okay, that's an important point, because h is the difference of differentiable functions. It's differentiable. Since it's differentiable, it's going to be continuous on any interval strictly contained in here. So what we have is that we know there's a point z where h prime of z is equal to the average rate of change over the interval c to d. But what is h prime of z? If I just take the derivative of h, that's f prime minus g prime, but h prime and g prime are both f. So this is actually, so h prime of x is just equal to f prime of x minus g prime of x, which is 0, because both of these are just f of x. So that means h prime of z has to be 0. But we're assuming that h of c doesn't equal h of d. So on the other hand, this can't be 0, because h of d minus h of c is only 0 if those two values are equal. This is a contradiction. So in other words, there's a problem with our assumption. So it must be the case that h is constant. So f of x is equal to g of x plus some constant, whatever that constant h of x is equal to. And so this is a little bit technical, I know, but I just am trying to give you a snapshot at why the mean value theorem is so important, because you're going to see later on The fact that antiderivatives differ by a constant is one of the most useful things we can use later on when we talk about integrals. But let's not get ahead of ourselves. Let's look at some examples. So this is another one of my favorite problems from calculus, because it's just kind of cool, kind of cute, and it really illustrates the heart of the mean value theorem. Now, I've never gotten pulled over getting a ticket where two police officers have used this method, but if I ever do, I'm going to be so happy because it's going to be so amazing because it's such a cool application of math to be able to do. So you should be careful and look out for this. But the idea is that you're driving down a road where the speed limit is 70 and there are two police officers. So let's draw a picture just so you can kind of visualize what's going on here. So I'll just put some blue lights. Here's police officer and police officer. Sorry for my subpar drawing skills. So here's the car, and then here's the car. Okay, so this is a span of 40 miles. Okay, so I'm here and I pass a police officer at 11:15. And now I'm clocked going 65 miles per hour. Then down here at 11:45, I'm clocked going 70 miles per hour. And that's all the information we have. Now the police officers are radioing each other and they say, okay, well, let's say that my car is orange. I'm the only orange car on the road right now. Okay, so police officer 1 says, oh, I see an orange car at 11:15 going 65 miles per hour. Radios over to his buddy, 40 miles down the road. And then at 11:45, this police officer says, oh, I see the same orange car. They're going 70 miles per hour. Now, to the average observer, you would say, oh, okay, great. Well, there's no way you're going to get a speeding ticket because you got lucky, right? You passed this first police officer going 65 and you passed the second officer going 70. No way they can give you a ticket. But second police officer pulls you over, hands you a ticket. Have a nice day, sir. So why is the police officer justified in giving you a ticket? Well, it actually has nothing to do with the two readings that the police officers get on their speedometers. It only has to do with the time you pass each police officer and the distance you've traveled in that time. So notice that the difference in time here is 30 minutes. Okay? So you have driven 40 miles in 30 minutes. So your average speed is what? Well, average speed, average rate of change of your position, is just how far you've changed in your position, so 40 miles, divided by 30 minutes. But now this is the same thing as 40, so this is miles, and this is minutes. That's the same thing as saying 40 miles in half of an hour. But 40 divided by half is 80 miles per hour. Now you're starting to see the problem. You averaged going 80 miles per hour. But what does that mean? The mean value theorem then tells you, and this is the key to understanding what the mean value theorem says. You have an average speed of 80 miles per hour. The mean value theorem guarantees you are traveling exactly 80 miles per hour at some point. Specifically between 11:15 and 11:45. So it's cool that you can just look at your average speed and know with certainty that there's a time you are driving exactly your average speed. That is what the mean value theorem is telling you. And if you ever get pulled over and the police officer used this method, you should find me and tell me, because I have been desperately looking for someone that's actually used this method, because I think it's brilliant. I think you could get so many people, because you see a police officer, you slow down, they clock you, you're not speeding, you speed up, and you see another police officer, you slow down. But if they use the mean value theorem, they could catch everybody that does that. So that's my 2 cents. But understand the mean value theorem, the heart behind the mean value theorem. Okay, so for this function, why does it satisfy the hypothesis of the mean value theorem? Well, this is pretty easy. This is a polynomial function. It's continuous everywhere. It's differentiable everywhere. So everything checks out. Okay? So polynomial, that's basically all we need to say, okay? Because polynomials are continuous and differentiable for all real numbers. So they're going to be continuous and differentiable on any closed interval. Now we want to find all the values of C satisfying the conclusion of the mean value theorem, or in other words, the values of C for which the instantaneous rate of change equals the average rate of change over this interval. So we're going to set f prime of C equal to f of 1 minus f of negative 1 all over 1 minus negative 1. Okay, so what is f prime of C? Well, f prime of x, remember that finding the derivative of a function is sort of like always necessary at this point. So at some point we're going to have to find the derivative, and it is 6x plus 2. So f prime of C is 6 times C plus 2. Okay? So let's see what f of 1 minus f of negative 1 is. Well, f of 1 is 3 plus 2 plus 5, so that looks like 10. And then minus f of negative 1, well, this is still 3 plus 5, but this is minus 2. So 3 plus 5 minus 2 is 6. And then 1 minus negative 1 is 2. So this is 4 over 2, which equals 2. Okay, so what we have is 6 times C plus 2 equals 2. Well, let's just solve for C. Subtract 2 from both sides. We have 6C equals 0, or C equals 0. So the mean value theorem guaranteed there was at least one value of C for which this is true. F prime of C is equal to the average rate of change over this interval, and here we see there's exactly one C value. C equals 0. Okay, so again, to justify that f satisfies the hypothesis of the mean value theorem, we just need it to be continuous on the closed interval and differentiable on the open interval, 0 to 2. So f is a polynomial. That's pretty much all we need to say. So no problem. It's continuous and differentiable for all real numbers. So let's take the derivative, because we know we need to do that. We get 3x squared plus 1. Okay, and we want to solve f prime of c equals f of 2 minus f of 0 over 2 minus 0, the average rate of change over this interval. So when does the instantaneous rate of change equal the average rate of change? Well, f prime of c is 3c squared plus 1. And then f of 2, that's 8 plus 2 minus 1, so that looks like 9. Okay, and then f of 0 is negative 1, so minus negative 1, all over 2. Okay, so this is 9 minus negative 1, which is 10. 10 over 2 is 5. So we have 3c squared plus 1 equals 5. Or in other words, 3c squared equals 4. So c squared equals 4/3. And then we're actually going to get two values of c here. So c equals plus or minus 2 over the square root of 3. But what we need to notice is that only one of these values of c is actually in this interval. So the only value of c that satisfies the conclusion, recall that the c needs to actually be contained in the open interval from 0 to 2. So that's going to be positive 2 over square root of 3. So actually, again, there is only one value of c satisfying the conclusion of the mean value theorem. Okay, so before we justify why this function satisfies the hypothesis of the mean value theorem, let's just take the derivative. So the derivative here, recall that cube root of x is x to the 1/3. So what we have is that this is 1 over 3 x to the 2/3. So I bring down the 1/3, subtract 1, we get x to the minus 2/3, but that's just 1 over x to the 2/3. So what this shows us is that f is differentiable everywhere except x equals 0. But that's actually okay. F is continuous. Everywhere. And that's just coming from the limit laws. I can take the limit of this function anywhere. It's just an algebraic function, just taking a root of the identity function. So there's no problem with continuity. Differentiability only is a problem at x equals 0, but remember that I only need f to be differentiable on the interior or on the open interval 0 to 1. So I'm actually okay that f is not differentiable at x equals 0. Everything's fine. So now let's find the value of c, or the values of c, satisfying the conclusion of the mean value theorem. So we have f prime of c is equal to f of 1 minus f of 0 over 1 minus 0. F prime of c is 3 times c to the 2/3. And then f of 1 minus f of 0 is just 1 over 1 minus 0, which is just 1. So we want to solve 3c to the 2/3 is equal to 1. Okay, so what do we have? Well, let's first divide by 3. So we have c to the 2/3 is equal to 1/3. Okay. And now what? Well, we want to raise both sides to the 3/2 power. Okay. So if we take the square root, if we cube both sides, we'll get 1 over 27. And then we square root, we're going to get plus or minus 1 over the square root of 27. And now, of course, we only want the value of c between 0 and 1. So the only value that's going to satisfy the conclusion of the mean value theorem is 1 over square root of 27. So again, let's take the derivative of this function before we discuss why it satisfies the hypotheses of the mean value theorem. So we know actually right off the bat that this function is continuous, except at x equals -2, which isn't contained in the interval we're concerned with. So that's no problem. So to take the derivative, we'll use the quotient rule. So it's x plus 2 times 1 minus x times 1 all over x plus 2 squared, low d high minus high d low, over low squared, which is, okay, x plus 2 minus x, that's 2 over x plus 2 squared. So this function is differentiable at every x value except -2. So specifically, it is continuous and differentiable where it needs to be, actually over this entire interval. So everything's great. So we're ready to look for the c values satisfying the conclusion of the mean value theorem. Okay, so we want to set f prime of c equal to f of 4 minus f of 1 over 4 minus 1. So the instantaneous rate of change equal to the average rate of change over this interval. And what is this? Well, f of 4, that's 4 over 6, so 2/3 minus, this looks like 1/3. So 2/3 minus 1/3, 4 over 6 over 1 over 3. So that's 1/3 over 4 minus 1, which is 3. So it looks like this is 1/9. And then f prime of c is 2 over c plus 2 squared. So we need to solve 2 over c plus 2 squared equals 1/9. Okay, so let's do it. Let's start by cross multiplying. So we have 18 is equal to c plus 2 squared. Now we'll take the square root, so we'll have plus or minus square root of 18 is equal to c plus 2 So c is equal to plus or minus square root of 18 minus 2. Okay, so now if we take the negative square root of 18 and subtract 2, that's going to be a negative number. So that's not going to be in this interval. So we want to take the c value that satisfies the conclusion of the mean value theorem for this interval to be square root of 18 minus 2. And because the square root of 18 is, well, it's less than 5 and greater than 4, then if we subtract 2, we know that this is going to be between 1 and 4. So here's our c value. Okay, so we're given the derivative of a function here, 2x, and we're also given a point on the graph of f of x. And we need to determine explicitly f of x. So here's how this goes. Well, first of all, we know that f of x has to be an antiderivative of 2x. So f of x is an antiderivative of 2x. So here's where you just have to do a little bit of thinking. So let's think backwards. What's a function whose derivative is 2x? Well, the first one that comes to my mind is x squared. So we know that f of x should be x squared plus, well, remember that all antiderivatives, so x squared is one of the antiderivatives of 2x, but all of them differ by a constant. So we know that whatever our f of x is has to be x squared plus, well, some constant c, some real number. And now the goal is to find c. Now, if we just said the derivative of f is 2x, that's not enough to actually specify what the c value is, or specifically what f of x is. But once we have a point on the graph of f of x, then we can actually nail down what the c value is. Because I know that f of 4 is equal to 5. So if I plug in 4 for x, I should get 5 for f of x. So this is f of 4, which is 5, but on the other hand, f of 4 is 4 squared plus c. Okay, but that means that 5 is equal to 16 plus c, or in other words, c is what? Negative 11. Okay, so now we know specifically what f of x is. F of x has to be x squared minus 11. And you can verify, it's always a good thing to do to check your answer, that if you take the derivative of this function, you do just get 2x. And also, if I plug in 4 for x, I should get 5, which I do. I get 4 squared minus 11, which is 5. So that's the idea of finding an antiderivative given some point on the graph of the function. Okay, so very similar situation here. We have the derivative of a function and then a point on the graph of the function itself. So we know the first step is to find an antiderivative. So notice, I can just think backwards. I know that sine and cosine have this derivative relationship. The derivative of sine is cosine, and the derivative of cosine is negative sine. So if I want a function whose derivative is sine, it seems like I should take Well, cosine would give me negative sign, so I should take negative cosine. Okay, so this is an antiderivative of sine, because if I take the derivative, I'll get sine, but I don't know which antiderivative it is. Okay, so I need to add on this plus c, because it might be translated vertically by some constant and still be an antiderivative. And to find c, we need to actually use this point on the graph of the function f. So we're given that f of pi over 2 is 3. So if I plug in x, I should get a y value of 3. But on the other hand, if I plug in pi over 2, I get negative cosine pi over 2 plus c. But what is cosine of pi over 2? That's actually 0. So I have 3 is equal to 0 plus c, or in other words, c is equal to 3. So then now I know exactly which antiderivative f is. It's negative cosine of x plus the constant 3. So pretty straightforward. And we'll see later, really the hardest part of this is just finding an antiderivative. Once we find an antiderivative, we're basically there. We just need to nail down using some algebra. But it can be pretty tricky because we're really not, as of right now, using any methods or techniques to find an antiderivative. We're really just guessing. Okay, so you can imagine that if a function was more complicated, it could be a lot harder to guess. But that's when we'll develop techniques to make more educated guesses, I guess. All right, so we're looking first for a function whose derivative is 1 over 1 plus x squared. Now, this one's a little bit trickier because maybe it's one of the more obscure derivative rules that you're going to have to remember. But I'm sure if I told you the answer, you would be like, oh yeah, that's a thing that exists. So recall that inverse tangent, if I take the derivative, what do I get? Well, I get 1 over 1 plus x squared. Okay, so that's sort of the takeaway. But same story. I don't know that the antiderivative is inverse tangent. I just know that it is inverse tangent plus maybe some constant that I should figure out. Because I know that the function passes through the point -1, 0. So if I plug in -1, well, I'm going to get 0. But on the other hand, I have tan inverse of -1 plus c. Okay, and so recall, this is a little tricky, but what is tan inverse of -1? Well, I'm looking for an angle between negative pi over 2 and pi over 2 whose tangent value is -1. That's negative pi over 4. So we have that 0 is equal to negative pi over 4 plus c, or in other words, c is pi over 4. But then our function, our antiderivative that satisfies, sometimes you say this initial data or passes through this point, is tan inverse of x plus pi over 4. And there it is.